Welcome to Algebra 1, Unit 9, Lesson 8.3, Multiplication Properties of Exponents. Pearson, Algebra 1, copyright 2009. I'm Mr. Pilarski, and our objectives today are, I will be able to multiply powers, and I will be able to work with scientific notation. First thing we need to look at is the property here, multiplying powers with the same base. When we multiply powers with the same base, it reads, for every non-zero number a and integers m and n, a to the m times a to the n is equal to a to the m plus n. Let's take a look at that again. Here we have this multiplication expression, a to the m times a to the n. First thing you want to notice is that they have the same base. They have the base of a, multiplying powers with the same base. The next thing to notice is they have different exponents. And the answer, or the simplified form of that, would be the same base, a in this case. And to find the new exponent, we add the exponents. When you multiply powers of the same base, you add the exponents. You may want to write that down. You may want to pause the video, and you may want to write that down. A to the m times a to the n is equal to a to the m plus n, means when you multiply powers of the same base, you add the exponents. So here, in this example, we have 3 to the 5th times 3 to the 4th. We can use the definition of exponents, repeated multiplication that is, and break this down to see why this property works. If we take 3 to the 5th, and I'm going to do that in blue, write that as 3 times 3 times 3 times 3. And here, the 3 to the 4th, we write that as 3 times 3 times 3 times 3. And by the definition of exponents, since this is 3 times itself 9 times, that does give us 3 to the 9th. And that's why this property works. Right here would be a mini proof, if you will. That's why we can add these exponents. So we have this base of 3. Our answer has a base of 3. And we add the exponents. It's like a little shortcut. Instead of having to write this out every time to get this answer here, 3 to the 9th, you can remember this little shortcut. In the second example here, it's more algebraic because it has a variable instead of a number base like 3. Here we have a base of h with an exponent of 2. Here a base of 9 with an exponent, or a base of h with an exponent of 9. We can see that we add the exponents in this case, 2 plus 9, and it is the same base. And the answer is the answer to the simple addition problem, 2 plus 9, which gives h to the 11th. And notice that the base is still h. So remember, when you multiply powers of the same base, you add the exponents. So let's take a look at example 1, which is going to require us to multiply powers of the same base. Rewrite each expression using each base only once. So we're going to apply that property that we just saw, that we just learned. 7 to the 3rd times 7 to the 2nd. Notice we have the same base now. And that base is 7. And the exponents are 3 and 2. So rewriting that with one base, the base is going to be 7. And the exponent we can write is 3 plus 2. We simplify this a step further by going 7 to the 5th, by completing this addition in the exponent. This is our answer right here, 7 to the 5th. In some cases, you may be asked to evaluate that not only write it with an expression using only one base, but you also may be asked to evaluate it. We'll see that in a later lesson. In part B of example 1, you can notice we have 4 to the 4th times 4 to the 1st times 4 to the 2nd. In each one of these cases, the base is 4. So we can apply that property again. Using the property, when we multiply like bases, we can add these three exponents, 4 plus 1 plus negative 2. And that will simplify with a base of 4 and an exponent. Now we have to do a little bit of addition here. 4 plus 1 is 5, and 5 plus a negative 2 is a positive 3. So the solution here is 4 to the 3rd. In the last example, we have 6 to the 8th times 6 to the negative 8th. Notice I underlined the bases in blue and the exponents in red. Since we have the same base, our solution is going to have a base of 6. And using the property, when multiplying two like bases, we add the exponents. And that does simplify to 6 to the 0 power, because 8 plus negative 8 is 0. And if we were to simplify that further, or evaluate, if you will, that would just be 1, because anything to the 0 power is 1, as we learned in the previous lesson. Example 2, multiplying powers in an algebraic expression. In this particular problem, or these particular problems, we move away from numerical expressions and we add in the idea of coefficients and like bases, and we're going to apply the same property of multiplying like bases, and we need to distinguish between what's an exponent, what is a coefficient, and what the actual base is. So in example 1 here, where we're asked to simplify, 3x to the 7th times 4x to the negative 3, the first thing I notice when I look at this example is we have a like base of x here. We do have two monomials being multiplied together at this point. The coefficient of the first monomial is 3. The coefficient of the second monomial is 4. And what we're going to do is we're going to take those monomials, we're going to multiply those separately over here. 3 times 4. Those are our monomials. Let me highlight those. I'll highlight those in orange, I believe. Nope, got green. The coefficients are highlighted in green. That's what I'm multiplying right here, 3 times 4. And we have a like base of x. And we have the base of x twice. And we need to add those exponents as we did in the previous example. You can do that in your head, or you could write it down as I am about to here. What I have here is 7 plus 3, or negative 3. 7 plus negative 3. And when I simplify that one step further, 3 times 4 is 12. And when I simplify that exponent by adding, 7 plus negative 3 is a positive 4. So I get 12 times x to the 4th. In part B, we have 2q times 3p to the 3rd times 4q to the 4th. When I read this the first time, what I noticed is I had two different bases. The first monomial is 2q. The second monomial is p to the 3rd. It's 3p to the 3rd, 3 times p to the 3rd. And that base is p. And in the third monomial, I have 4q to the 4th. That base is q. So I notice I have two different bases. I have a base of q and a base of p. Actually, I have two bases of q and one base of p. So I'm next going to focus in on those coefficients. After I identify the fact that I have two different bases, p and q, or two different variables, p and q, so I focus in on those coefficients. I can simply multiply those coefficients together, 2 times 3 times 4. you may even do that step in your head. 2 times 3 is 6, and 6 times 4 is 24, or you could write it out like this. The way I write this out here then is in alphabetical order. P then Q would be alphabetical order for now. So that'd be P to the third times Q to the 1 plus 4. And if you're asking yourself, where's that 1 coming from? That's coming from the fact that if there is no exponent showing, that exponent is a 1. So simplifying this, 2 times 3 is 6, times 4 is 24. P to the third. Sorry, lost connection there for a second. So, as I was saying, we're going to simplify 2 times 3 times 4, which is 24. P to the third. Q to the fifth. So this is the simplified version of this expression. Example 3, multiplying numbers in scientific notation. Simplify 3 times 10 to the negative third times 7 times 10 to the negative fifth. Write the answer in scientific notation. This problem does have a little twist at the end, but let's first multiply these two numbers. And it really boils down to multiplying the number factor in the number expressed in scientific form, and then multiplying the powers of 10 by using the idea that the powers of 10 have like bases. So using the property we saw at the beginning of this video math lesson. So writing this problem down, we need to multiply the 3 and the 7. We multiply the A part of scientific notation. And then we'll multiply that by the powers of 10. And since they're like bases, we take their exponents and we add them. Be negative 3 plus negative 5. 3 times 7 is 21. And that's times 10 to the negative 8 power. Remember, we add those exponents because the bases are the same. Now, this is not the answer. Here's where you need to be careful. This is not the answer. This is not the answer because this answer is not in scientific notation. You may think it's in scientific notation, but it's not. It's not in scientific notation because the number part, the A part of scientific notation, has to be a number greater than or equal to 1 and less than 10. It has to be between 10 and 1, and it can be 1. It can't be 10, but it can be 1. So to do that, we need to make 21 into 2.1, and we do that by moving the decimal, which resides to the right of the 1 in 21, one time to the left. Or, in other words, multiply that by 10. So we have 2.1 times 10 to the negative 7th. When we move to the left, when we move a decimal to the left one time, it's like multiplying by 10. If we move it 2 times, it's like multiplying by 100. It's powers of 10. So the correct answer here is 2.1 times 10 to the negative 7th. Where you might get fooled on a multiple choice test is this is listed as one of the answers, 21 times 10 to the negative 8th. But it's not the correct answer. 2.1 times 10 to the negative 7th is. Example 4, real-world problem solving. The speed of light is 3 times 10 to the 8th meters per second. If there are 1 times 10 to the negative 3rd kilometers in 1 meter and 3.6 times 10 to the 3rd seconds in 1 hour, find the speed of light in kilometers per hour. When I first read this problem, I think this is a unit analysis problem, or dimensional analysis, it's also called. I call it that because what we're working with mainly is units. We're given the first sentence, the speed of light is 3 times 10 to the 8th meters per second. That's what we're given. So I write that down. So it's 3 times 10 to the 8th meters over seconds. The next part that I'm given is 1 times 10 to the negative third kilometers per meter. And it just so happens I want to change this meters per second into kilometers per hour. So this unit is given really conveniently, because it's 1 times 10 to the negative third kilometers per meter. So that'd be kilometers per. The per is like a division sign. It translates into division. So it's kilometers per meter there. And finally, 3.6 times 10 to the third seconds in 1 hour. Forgot to write the 10 to the third. And the reason this is an H, it doesn't look much like an H, but it is. It's an H. And since we're asked for kilometers per hour, this works out great. The meters divide out, because they're on one in the numerator, one in the denominator. And the seconds divide out, leaving us with exactly what we want, kilometers per hour. So to simplify this, we multiply what's in the numerator, because what is in the denominator is a 1. 1 second, 1 meter, 1 hour. So all we have to do is multiply these three numbers. So we multiply the three number parts here. We multiply the 3, the 1, and the 3.6. And we can write that out as 3 times 1 times 3.6. Now, don't really need to write the 1. I wrote it there to prove a point that it's there. You don't need to write it. And that would be times 10 to the, and since each one of these bases is base 10, all we have to do is add the 3 exponents. All we're going to have to do is add the 3 exponents, and this ends up being real easy addition. 8 plus a negative 3 plus a positive 3. The negative 3 and the positive 3, they become 0, which just leaves you 10 to the 8th. And so we have times 10 to the 8th on the right for the base 10 of the scientific notation. And when you multiply 3 times 3.6 times 1, that gives 13.68. Now, it doesn't say to express the answer in scientific notation, but usually you do. So this is not in scientific notation. I want to put the answer in scientific notation. Remember, this right here, this line right here is not scientific notation. So what I'm doing right now is putting it into scientific notation. And to do that, I need to take 13.68 and make it 1.368. Now, not only does it affect that, the number part, it also affects the exponent, which is going to be to the 9th, because we're multiplying that by 10, or 10 to the 1st. So we add 1 to 8 to get 9. And the units on that would be kilometers per hour. So we fill in the units, kilometers per hour. So the speed of light in kilometers per hour is 1.368 times 10 to the 9th, or 1.368 billion kilometers per hour. So the speed of light is pretty fast. This has been Mr. Pilarski on multiplying powers by the same base. Remember, when you're multiplying powers by the same base, you add the exponent. So if you have a to the n times a to the m, you're going to simplify that by going a to the n plus m. If this video has helped you, feel free to leave a comment or like, give me a thumbs up. This has been Mr. Pilarski. Thanks for watching. Bye-bye.